information with a focus on quantum cryptography. He is a fellow of the National Academy of Sciences, Institute of Electronics and Telecommunication Engineering, and Optical Society of India. He is a visiting scientist at Palak University, Czech Republic. He is also a member of the editorial board of Quantum Information Processing Springer. He guided 6 PhD students and a number of postdoctoral fellows. And at present, he leads a research group focused on quantum optics and quantum information with specific interest on quantum cryptography. He has also completed several DST and DRDO funded projects, and at present, some ongoing projects, some projects are ongoing. And he has active research collaboration with different research groups in India and abroad. He is also a recipient of 2017 Sri O.P. Vesin Award in the field of electronics and information technology. So I would like to invite Professor Anirban Pathak to illuminate us with his vast experience in the field of quantum information theory. The title of his talk is Let's Get Entangled with Entanglement. Professor Anirban Pathak, please.
Thank you, Shatabhrata. I mean, am I audible and visible properly?
Yes, Anirban.
So, before I start, I would like to thank Professor Prashant Panigrahi and his colleagues and students for arranging this nice meeting. So we have a long memory of this meeting from pre-corona days and when it was mostly in physical mode and spending time in ISER, and most of the time the participants were very young students, means were planning to do quantum information but not. So I made my talk keeping them in mind, and as the title suggests, let's get entangled with entanglement. So this is already 3 weeks of the school has already over, means because it started from May 8. So many people have spoke about entanglement. And my talk will be about many facets of entanglement that appears in many directions in our work. So it will be varied, it will be wide, and I'm not sure whether I'll be able to cover everything that I have put in slide. But then I primarily want to talk about entanglement routing and pose some questions, thought process, which is not in the or expose the students and participants to some somewhat open questions or not so much discussed things, issues about entanglement. So to us, entanglement is mostly like a resource and which is very useful in achieving QIQT kind of quantum cryptography, different protocols of quantum cryptography for achieving some kind of device independence. So if it is not entanglement, say for using non-local states. So beyond that means, or the applications like teleportation, dense coding. So beyond that, how the issues in which entanglement appears in our work, so we'll give glimpses of different facets through which entanglement appears in our work. And that's the reason the talk is called Let's Get Entangled with Entanglement. So we'll talk about many facets of entanglement and try to get the audience or entangled with the activities we do involving entangled states. So to begin with, I'll start with the basic definition of entangled state. So entangled states we mostly see as inseparability. So if I have a quantum state xi AB of 2 part and I write xi A tensor xi B, then it is separable. So for example, 1 by root 2 0 0 plus 1 1 0. So you can take the second 0 as common. So B particle is in state 0 and first particle is in a superposition of 1 by root 2 0 plus 1 by root 2 1 or in a plus state. Whereas the next example is of a Bell state where you cannot write it as. So in this definition, if you consider this as the definition of entanglement, then entanglement means inseparability. What else? We can see that this is superposition between two states, and this superposition is allowed in tensor product space. So if superposition exists and tensor product structure exists in a theory, then there can be entanglement. Now, the question is this superposition in tensor product space, is it quantum? Or there is a classical analog of it also. So whether entanglement is, means all the way we discuss in this kind of conferences is that entanglement is quantum, but as far as this definition is concerned, inseparability.
Anirban, sorry for the interruption. Your slide is not moving.
Oh, okay. I mean, So this is a common problem, but I don't see the share the entire screen button. Okay. So can you see the second slide now?
Yeah.
Uh, so entanglement is, so just check that it's changing. Means now is it changing now?
Yes, it is changing.
Okay. Uh, So in slide share mode, it means sharing the file is not working, but when we share the entire screen, it's working. Anyway,
But you were entangled with us, no?
yes. So we have to share the entire screen. Entangled states are more common than separate states. Means that's very easy to understand when I define a concurrent. Suppose you have a state A00 plus B01 plus C10 plus D11, and then it will be entangled only, separable only if AD is equal to BC, means, or concurrence will be 0 when AD is equal to BC, but that's very specific case. In most of the choices of AD BC means ABCD, then it will be entangled. So entangled states are very common, but we are interested in another question. Whether this is appearing as superposition in tensor product state, is it unique of a non-classical theory or quantum theory or not? The answer is not. So first thing I want to note that superposition exists in any theory where governing equation is a linear differential equation. So Maxwell's equation is also linear differential equation. So superposition we see in the classical world, and that's appeared through interference. Then is the tensor product space unique to quantum mechanics? The answer is no. In polarization theory, those who are familiar with the optics, this is visible. So then the first paper I came across about this classical kind of entanglement was of Alfredo Lewis, and here they examine classical version of entanglement between spatial and polarization degrees of freedom. So before getting entangled to entanglement, we just wanted to tell the audience that I'll pose questions, touch issues which are not that much discussed. So there is a classical version of entanglement too. But classical entanglement can be defined as the lack of separability. And in the beginning itself, I mentioned that if inseparability is considered to be the definition of entanglement, then entanglement is also there in the classical world. So this is inseparability of the cross spectral density tensor in spatial and polarization components. Now, this was the first idea. Then almost simultaneously, Eberle and Simon's paper come, and Simon did not tell it classical entanglement. He called it non-quantum entanglement. And actually, the Lewis paper showed only that there is a classical version of entanglement, but was not used for anything. But now Simon paper use it for this classical entanglement or non-quantum entanglement or inseparability between polarization and spatial degrees of freedom of an electron magnetic beam whose polarization is not homogeneous, to provide a physical basis to resolve a problem which was long lasting in optics. And it appeared again in Eberle's work almost simultaneously. So the message is that it's not unique. Entanglement is not unique of the quantum world. So actually, when you develop quantum mechanics or any theory, so there is an axiomatic structure. So there are axioms, and these axioms can be placed hierarchical manner. So superposition exists in classical world. There is nothing quantum. So this can be a classical assumptions means or axiom. Then tensor product space exists. So there is a kind of entanglement. Now you add on feature of non-classicality, and that can be done in hierarchical manner. So in one of our paper with Srikant, we added incompatibility and uncertainty as the Q1 or the first axioms of quantum mechanics, then contextuality, then entanglement. So if you want to see it in a lucid manner, suppose you have a classical entanglement, you cannot do teleportation, dense coding, anything. Now you add that you are making a non-classical theory, but not a quantum theory, not quantum mechanics, but not a classical theory. And you just add measurement on collapse on measurement. So collapse on measurement will ensure that you can have in this toy theory, you can have BB84 kind of protocols of cryptography, but nothing else. Now you allow that, say, non-locality you add, or entanglement you add, then you add non-locality. So the more features of a non-classical theory you will add, you will have a new toy theory where you can do certain things, but still you may exclude Q5 or indistinguishability. So this kind of toy theories people discuss, and there are toy theories which can contain entanglement. So entanglement is not unique of quantum mechanics. Now, okay, how do you measure entanglement? So by now in 3 weeks, many people must have used concurrence, negativity, etc. So the other point we want to note that there is no measure of entanglement which is unique. And if you choose more than one different measures of entanglement and plot like this. So here in this plot, we put concurrence in one side and negativity in one side. But this is the non-classicality of a qubit. So a qubit cannot have entanglement, of course. So what we are doing to measure non-classicality, there is a trick that you insert a non-classical state, single mode non-classical state from one port of the beam splitter and vacuum state from the other port of the beam splitter. If the state is non-classical, the output will be entangled. And then output you are measuring through concurrence or negativity. Now you see, suppose I have two states, A and B. So A is where my mouse is, and then its concurrence is 0.3 and negativity is about 0.1. Now you choose a state just along the linear line above 0.3 of negativity. Then you see that its concurrence is less than the first state A, but its negativity is more. So you cannot consider that, tell me, order the states A and B, which one is more entangled. So A is more entangled as far as concurrence is concerned, and B is more entangled as far as negativity is concerned. So there is, of course, we know that for tripartite entanglement, there is issues with the measure, but there is this non-monotonic nature is present for almost all measures of non-classicality, not restricted to entanglement. So this is the second point which I would like to draw attention, that entanglement exists in classical world. The measures of entanglement has issues and open problems, and this is not restricted to only the measures of entanglement or non-classicality. This is true for measures of coherence also. They are not monotone of each other. Well, now we talk about something else, which is very interesting. So entanglement, sudden death. So sudden death and revival in physical system is observed very frequently. So there is nothing unique, and there is nothing unique that we people like us, means who came from quantum optics background to quantum information. So our favorite model is Jaynes-Cummins model, which is studied for so many years, but still it gives new papers. So Jaynes-Cummins model, there are some test beds. So X state is a test bed. Here I have shown a particular X states. So this is maximally non-local mixed states, which is written as M and MS, and X can have these values. So, and why this is called a X state? If you see that only the diagonal term, like if you make a cross with your finger, the X, the diagonal terms have non-zero element and all other elements are zero. So this is called X state. So for now, this states I'm measuring the concurrence, and concurrence is defined as 0 and then square root of lambda 1 minus lambda 2. So these are the eigenvalues of the matrix, state matrix. Now, and of course, arranged in sequence. So if you see that this max, so who defines that this is entangled or not? So definitely the second term is square root of lambda 1 minus square root of lambda 2. So this term defines whether the state is entangled or not. So what we are measuring, maximum of 0 and this quantity. So if the second quantity is positive, the state is entangled. So what this 0 is doing here? So it is just forcefully making the whole thing positive. That if you plot, you will see the positive part only. And even if square root of lambda 1 minus square root of lambda 2 minus square of lambda 3 minus square root of lambda 4 become negative, that will not be plotted. That part will be 0. So you see that this positive part I can see, and then so it died here, the entanglement, and at before 0.35 in the sub figure, and then it recreated from 0.4. Now the question is, we say this is a sudden death. So entanglement sudden death refers to the vanishing of entanglement at a point with a discontinuous derivative. So is it actually happening, or entanglement sudden death is a manifestation of our definition where I put this 0 where it becomes separable and forcefully made this function non-negative. So if you drop this 0, then what will happen? Then the function will go in the bottom part and then come. So what happens in this case? So if the concurrence means, if you call it some modified concurrence, if it is negative, then the state is not only separable, it is mixed. So pure separable states and mixed separable states, for pure separable states it is 0, for mixed separable states it is negative. But then this discontinuity will not be visible. So I left this discussion with a question. Of course, these plots are from our paper where we claim entanglement sudden death in X states. We do entanglement sudden death in context of Jens-Cummins model regularly. But here the intention is to leave a question in your mind whether entanglement sudden death really happens, or it's a consequence of the definition of concurrence, or an artifact introduced by the definition of concurrence, which is intentionally bounded by introduction of this term 0. So when you write max 0 comma this, so you made it lower bound at 0. But that, of course, that's a nice way to measure your entanglement. But is the entanglement sudden death is visualized because of this or not? So okay, now in quantum optics we see entanglement through certain criteria. It's in daily life inequality is bad, but here we often use inequalities. So here I show some inequalities. So first one is called Duan's inequality, and these are written in terms of field operators. Then there is Hillary-Juberry criteria for entanglement. There are more than one criteria, and usually we write a Hamiltonian like one shown in the right hand side bottom, and then apply Shane-Mondel approach. So what we do here, so we find out A dot, A double dot, A triple dot, etc. by applying Hamiltonian comma A. So H comma A leads to A dot, H comma A leads to A double dot, and so on. So I have time derivative of the field operators, and then I can put it in Taylor series. And if we do so, then what we get a short time approach. But in Shane-Mondel approach, we continue doing this until new term comes. So when I have all the terms involving a dagger to the power something to times a to the power something, I collect all of them terms and give them a coefficient, say f1t, f2t, and put it back. So I get a set of coupled differential equations and solve those coupled differential equations to obtain solutions. Once I have these field operators, at, a dagger t, bt, b dagger t, then I can apply in this criteria and find out. It of course involves a lot of operator ordering, but you can find out signatures of entanglement. So what are the physical systems where we see signature of entanglement? So one such system is shown here in the right top. So this is a system and there are two probes. So these are optical couplers. So I just show in next few slides some examples where we see entanglement. So these are different ways that entanglement appears in our work. And as I mentioned that when I came from quantum optics, so quantum optical systems always interest me. So what we are showing here is in the right hand side top is a Raman process. So this red line is showing a pump. So pump is of frequency omega A and is taking this electron from here to here. And then B dagger is showing a creation of a photon of frequency omega B. So this is the Stokes. And then you have phonon mode, which is shown by C, and D is the anti-Stokes mode. Now, the question is, if we describe this as by Hamiltonian shown above and solve it in Shane-Mondel approach and apply to Duan's criteria, etc., or Hillary-Juberry criteria, do I see entanglement? So in the left top, you can show that Stokes mode get entangled with photon mode, then pump and anti-Stokes get entangled, and so on. So the negative part is showing entanglement. Stokes and anti-Stokes get entanglement. And as I told you that sync entanglement is more common than separability. Separability is relatively rare. So physical systems, when you study it is expected that you will see entanglement after interaction in most of the cases. So this is a different kind of systems. This is called atom-atom BEC. So what is atom-atom BEC? That there is a Bose-Einstein condensations and one mode is this well. So this is nothing but a double well separated by this barrier. But when a particle goes from annihilates from left-hand side mode, say B mode, it creates one particle in right-hand side mode. So what will be the corresponding things in the Hamiltonian? It will be like one created, then the other one is annihilated. So the terms will be like A B dagger plus B A dagger, which is also often used for beam splitter, for optical coupler. So here we are talking in terms of BEC. So in case of this, total number will be conserved, and we can again apply the same kind of trick and see that whether higher order entanglement is happening and such things. So entanglement is reported in So there is, it's showing some quantum genoparameter, and this is the Chi2 nonlinear coupler, and the lower one is Chi1 nonlinear optical coupler. And we can see this entanglement. Whenever the blue part is entangled, the red part is not. But we are not interested in discussing here that for which particular choice of parameter it get entangled or things like that. We are interested to just to show you that, well, in quantum information, we often use that. Means most of the time we draw a BBO crystal and a light is coming, and outside the BBO there are some cones and you get entanglement. So that's not the only way to generate entanglement. There are physical systems which generates entanglement, and there are ways to study them. So we have already mentioned in this context about Hillary-Juberi criteria. Now, I want to introduce a mathematical trick which leads to Hillary-Juberi criteria. So this trick is called majorization. So let's start from alpha. So alpha here is a sequence. So I move slowly, and for next few slides, I'll be very slow, and if you have any query, stop me there itself. Don't wait for the lecture to be completed. So alpha is a sequence, say alpha 1, alpha 2, alpha 3, and it's a non-increasing sequence. And alpha prime is another non-increasing sequence, and the sequence are such that sum of alpha I is sum of alpha I prime when you take all the terms. So if it happens that if I take the first term, alpha 1 is greater than alpha 1 prime, alpha 1 plus alpha 2 is greater than alpha 1 prime plus alpha 2 prime, and so on. But alpha 1 plus alpha 2 plus till alpha m, when I take all the terms, then the sum is equal. So let's look at an example of majorization. So if this is the case, then I say that alpha majorizes alpha prime. Okay. So now if I take the state, say this is my sequence 3. So when there is no term, then I will consider it to be 0. So 3 is greater than 2, and 3 plus 0 is greater than 2 plus 1. So 3 majorizes this sequence to 1, or 3 comma 0 majorizes 2 comma 1. Next sequence is 1 comma 1 comma 1. So I have to read it. I have to read it like 3 comma 0 comma 0. So then 3 greater than 1, 3 plus 0 greater than 1 plus 1, 3 plus 0 greater than equal to 1 plus 1 plus 1. So 3 majorizes 1, 1, 1. Similarly, look at 2, 1, 2 greater than 1, 2 plus 1 is 3 greater than 1 plus 1 when I take 2 terms, and when I take 3 terms, then I read it like 2 plus 1 plus 0 greater equal to 1 plus 1 plus 1. So it majorizes. So I have some more example. Now, Muhirad inequality tells you that if a1 to the power alpha 1, at to the power alpha 2, and so on, and here alpha is a sequence which majorizes alpha prime sequence, then this left hand side will be greater than right hand side. So we can write expectations values in this way and make that claim that if the opposite expectations happens, then the weight factor, or P alpha, which is a quasi probability distribution, must be negative to change the sign. So this is the case where we get non-classicality, because the definition of non-classicality is when P function becomes negative. And this is how JIIT criteria is obtained. So that's the link of this to entanglement. But now I will take this majorization trick to a very interesting problems called entanglement routing. So far, normally in the lectures, you must be familiar with Eckart's protocol and so on. So we have, or you have been talked about teleportation, dense coding, where entanglement is already shared between 2 points, and you are using the shared entanglement for achieving tasks like teleportation and dense coding. But now think that this is a 4x4 grid network. So this kind of network you see in front of your phone, where you have give your sign for opening the phone. So this is a grid network, which is a 4x4 network, and 1 and 16 is not entangled, and I want to get them entangled. Now, option would have been that if there were quantum repeater, then quantum repeater could have increased the distance and get it done. But there is no repeater, but repeater-like protocol exists, which we call repeater protocol. But we will come to repeater protocol later. But now first, the task is that I have to create entanglement between 1 and 16. So there are protocols. I will describe the protocol. But now I just want to show you one application of majorization in this kind of problem. So where this is needed for entanglement routing is needed for achieving quantum internet. for increasing the distance, for doing distributed quantum computing, and many other tasks. So we want to go from 1 to 16. So there are several paths. So one path is that you have, if you are not seeing in mobile, then probably you can see that there is a red dot line which is connecting 1 to 5, 5 to 9, 9 to 13, 13 to 14, 14 to 15, 15 to 16. So I want to write a path vector for this. So how do I write the path vector? So I write the path vector that how many steps you go in one direction before changing the direction. So in this case, I have gone 3 steps, 1 to 5, 5 to 9, 9 to 13. So I write 3, you see in the top. Then you see the next one from 13. So figure A, 13, you are going to 14. After changing the direction, you are going upward 3 steps, 14 to 15, 15 to 16. So we write 3. So then that's it. You reached 1 to 6. So what is my path vector? So 3, 3, and rest of the terms is 0, 3, 0, 0, 0. Now you look at the figure C. So in figure C, we are going from 1 to 5, 5 to 9, and then upward. So 2 step in right, then 1 step upward, 1 step right. So we write 2, 1, 1, and then 2 step right. So 2, 1, 1, 2, 0, and then 0, 0. So probably you understand that how we are writing this path vector. So next figure is E, where I am changing the path vector after every step. So 1 to 5, going towards right, then 5 to 6 go up, then 6 to 10 right, 10 to 11 up, 11 to 15 right, and then 15 to 16 up. So this is 1, 1, 1, 1. So what we see that 3, 3, 3, 0, 0, 0, 0, this path vector majorizes 2, 1, 2, 2, 0. So because in every case, the total number of steps is 6. So 3 greater than 2, 2 greater than 1, 3 plus 3 is 6, greater than 2 plus 1, 3, 1 plus 1, 2, and so on. Now, if now we apply a X protocol, I'll describe X protocol in next slide. So, but you see the outcome. So what happens? My target was to create an entanglement between 16 and 1. You see in B that I have created that, but what I left with is a 2 cross 2 grid. But when I do the next one, along the next path, I apply the X protocol, this dotted red path, which is shown by this path vector in C, then I get the D. So you see the remaining part for my is larger. So larger amount of quantum state or quantum resources is left with me so that I can do future calculations. And in F, I have left with the 3 cross 3 grid. So which one is best? I must do the third one. So the path which has been majorized by all other is giving the best result. So this should be, if the path length is same, it's taking the 6 steps. So this one is giving me better result in terms that I'm creating the entanglement between 1 and 16, but the remaining resource is quite unchanged. It has not collapsed. It has not been, so I can use it for future. So that's a nice example of majorization. So this is in a very recent, this is from a very recent works of ours. So where we proved several theorems, but now I want to do this entanglement routing problem in a bit detail. So to do so, I have to make some definitions, but definitions may appear a bit clumsy, a bit difficult. But when I will do examples with this kind of figures, you will find that it's pretty easy to follow. So first I define a graph. So what is a graph? And the kind of graph we are interested is undirected finite graph. So you see these grids were my graph. So these grids were graph where each node is connected to some other nodes. All nodes are not connected. So there are vertices. So in this graph, there are 16 vertices and several edges. So 16 to 15 is a line, which is an edge. 16 to 12 is an edge, but there is no edge between 16 and 11. Okay. And no, there is no loop that something started from 16 and come back to 16 or, so that's a simple graph. So a simple graph is made up of vertices V, set of vertices and set of edges. A simple graph is without any loop and multiple edges connecting the same pair of vertices. So same pair of vertices are connected by only one edge. So the set of all vertices having a shared edge with a given vertex A is called the neighborhood of A and is defined by NA. So if you take now the say 0.7, so who are the neighbors of 7? So all those things which are connected. So 8 is neighbor, 3 is neighbor, 11 is neighbor, 6 is neighbor. So that set of 8, 3, 6, 11 is my neighborhood set NA.
So Anirban, So is the vertex represent a quantum system?
That not till now. That will be in the next slide.
Okay.
Till now, I'm defining a graph, undirected finite graph mathematically. So this up to this is a mathematical structure. So when I will introduce graph state, then I will add one qubit to each node. So until I do that, this is still a classical, means it's a mathematical structure, means it can be classical, it can be quantum, anything. So now we are defining vertex deletion. So deleting a vertex V results in a graph where the vertex V and all the edges connected to it are removed. So that's very simple to visualize. You have a graph, say, suppose you apply a vertex deletion on 4 in the figure, means where my mouse is, the 2x2 grid. So then 4 will also be deleted. The connection with the 8 and connection with the 3 will be deleted. So I'm left with a line graph that connects 8, 7, and 3. So this is vertex deletion. So then there is something called local complementation. So a local complementation is an interesting operation. So like LCV is a graph operation specified by a vertex V, taking a graph G to a corresponding graph on which, like LCV is an operation is applied on G by replacing the neighborhood of V by its complement. So what do we mean by complement? So neighborhood we have already defined. So if there is an edge, the edge will be removed. And if there is no edge, the edge will be created. So I repeat. So local complementation means I choose the vertex. If the vertex is connected to nearby nodes by edge, that edge is removed. And if there was no edge, the edge will be created. So acts on the neighborhood of a vertex by removing edges if they are present and adding missing edges. Then the last definition which I need is vertex minor. A graph H is called a vertex minor of G if a sequence of local complementations and vertex deletion maps G to H. So this is my background. It may seem difficult, but we'll show that with an example that it's not really difficult to follow. Now, answering to Shatabrata's questions. So I have a simple graph G, and now I'm adding a graph. So far it was mathematical. A graph state is defined on a Hilbert space. So now it is becoming quantum, and I'm adding a single qubit states to each vertices. So each vertex in V is assigned a qubit in the state plus, and then we apply a control Z operations as follows. So then the state which is created is called graph state G. So all the things now I am doing is we are looking at what happens if I do X measurement, Y measurement, and Z measurement. So that means you do a measurement in X basis, you do a measurement in Y basis, and you do a measurement in Z basis. What are their impact? So what I have told, so if you do a Z basis measurement, it creates vertex deletion. So it leads to graph G minus V. If I do a Y measurement, it does something like local complementarity and followed by a vertex deletion. And we do X measurement, it does this sequence of operations. So X measurement, Y measurement, and Z measurements are my basic tools through which I can do local complementations and vertex deletions. And in what follows, I will do only these things. And then we'll count that how many X measurement or how many Z measurement is required. The more measurement is required in a protocol is bad. So the lesser measurement is required, the protocol is good. And I will also try that to design the protocol in such a way, entanglement routing scheme in such a way that after entanglement routing, I'm left with larger amount of quantum resource, which I have shown through majorization. Okay. Now I show some nice example which will help you to understand it clearly. So I'm going slowly. I understand that the entire lecture will not be finished, but let's do justice to whatever we are showing, that let it be done properly. So here is a 3x3 grid, and I am interested in creating entanglement between 1 and 9. So now I have to find out the shortest path with a minimum neighborhood. So let's take the path we are taking is 1, 4, 5, 8, 9. It's not a unique path. So 1 to 4, 4 to 5, 5 to 8, 8 to 9. So it's a 1, 1, 1, 1, 1, 1, 1, 1 path as far as the path vector is concerned. So it will majorize by other. So neighborhood of 1, 4, 5, 8, 9 are the one. Who are the neighborhood of 1? Now you see that 1 is connected to 2 and 4. So 2, 4 is the set which is neighborhood of 1. Let's look at the next term, 4. So 4 is connected to 1, 7, and 5. So 1, 5, 7 is the neighborhood. So similarly, we find out the neighborhood of next term 5. 5 is connected to 4, 2, 6, and 8. So 2, 4, 6, 8 is the neighborhood. Now we make a set of all these neighborhood and I get 1, 2, 4, 5, 6, 7, 8, 9. And count out the cardinality of this set. So cardinality of this set is 8. So 8 is the neighborhood of this path. So now I make another path and check if the same distance path, it has a lower number of neighborhood or cardinality of the set, combined neighborhood, then we choose that path. So this is how I choose the path. Now the protocol, the simplest protocol is to find the shortest path connecting the two nodes with the smallest combined neighborhood. So this may not be unique. Then perform JIIT measurement on the nodes that do not lie on the path. So what the JIIT measurement does? JIIT measurement deleted the vertices and connection. So in our case, what is not in the path? So you see 1 to 4 you are going, and then 5 to 6, 8, and 8 to 9. So 3 is not in your line, 6 is not in your line, and 7 is not in your line. So you do vertex deletion on 3, 6, 7. So when you do vertex deletion on 3, so what happens? The point node 3 has been vanished, as well as the connection between 3 to 2 and 3 to 6 has been vanished. So what you will finally left with after removal of these things, that 1 will be connected to 4, 4 will be connected to 5, 5 will be connected to 8, and 8 will be connected to 9. So that is my figure B. So this is the repeater line. And now the task remains is I have to do sequential measurement and remove this. So first I remove 4. So I apply a local complementary operations. So which will X operation, what Z operation deleted the vertex. Now X operation is doing what? When I apply X operation on 4, it removes 4 and the edges. So 1 and 5 gets connected, and 4 is removed, and naturally connection between 4 to 1 and 1 to 5 is removed. So next step I do the operation on 5. So then 1 and 8 get connected and 5 is removed. Next I apply operation 8, and then 1 and 9 get connected. So this is how it works. So this is working along a repeater line. So this is called repeater protocol. So this was the first protocol known for entanglement routing, which I have explained. Now we can show that this could have been done in a better way. So the next protocol was proposed by Isert, Han, and Papa, and this was like this. So you have a grid network, and we apply just X operations along 4, 5, and 8, and we lead to this. And you see that number of operation is also less, and in X protocol, and then you have a 2x2 grid left. So this is better because the number of operation is also less, and you are preserving the resources for future operations. So how is the protocol defined? Find the shortest path between two nodes. So keep in mind, because I will show that shortest path will not always give you the best result. Two nodes with the minimum combined neighborhood, say path 1, 4, 5, 8, 9 as shown previously. Perform X measurement on all the intermediate vertices. Perform Z measurement on neighboring vertices, which is not required in our case. So the theorem the Isert and others prove is that this is at least equivalent to the previous protocol, and times it can perform better. So if it is not better, at least it is not, this protocol is not worse than, and in this particular case, you can see that this is better than the repeater protocol. So we have two protocols. Now, what we have done, so far everything was in Bell state. So our results are generalizing this to n-partite state. So we are talking about performing quantum internet, performing distributed computing. So n parties may involve. So we are showing that a particular case where extraction of GHG n states, so n-partite GHG states will be possible. So it is possible to extract an n-partite GHG state from a graph state Z when the underlying graph has a repeater line as vertex minor. So vertex minor I have already defined. And what kind of repeater line? Connecting all n nodes of the final GHG state with an extra node in between every pair of n-2 intermediate nodes. So this idea will be very shown clear. So look at this figure A in the right. So 1, 4, 5, 6, 9, 12, 11, 10 is my line. Now we just do the vertex deletion and I make it a ring-like structure. So in this, you see that between 12 and 6, there is a 9, and between 6 and 4, there is a 5. So which one is redundant? 11 is redundant because I needed an extra node between, except the last one. So extra node in between every pair of n-2 intermediate nodes. So between the last nodes, this 11 was not required. So just by vertex deletion, you remove 11. So what you left with this, and then now you do local complementary operations on 9 and 5. So you will get a JIIT state involving 10, 12, 6 and 4, 6, 4 and 1. So this is a particular case. We have done several such cases where stepwise we have shown, means that how, I mean, what I have shown here, that it's directly that if you show every step how this will work. But now in the right hand side, I show that there is a smarter way of creating JIIT 5 step. So I hope, means till now, till last slide, I was very slow, so we could arrange the protocol. So the takeaway message is that we have now a smarter theorem than ISAT, Papa, and paper for performing entanglement routing. But these are not, these are generalized in the sense that I can do entanglement sharing for JIIT in the n state, whatever with the value of n. But this is restricted to grid network. There can be other kind of networks, and other kind of networks can have other kind of issues also. So next one, I want to introduce to you to such an issue of entanglement routing. So first thing I mentioned, that is shortest path always good choice? The answer is no. So here, without describing the entire protocol, because by now you learned the protocol, I'm just showing that this is the shortest protocol path, 2, 5, 8, 11. And you combine neighborhood, etc. You calculate, I want to create entanglement between 2 and 11. When I create, everything else gets destroyed. Now I choose a longer path, 2, 1, 4, 7, 10, 11. And after application of X protocol, I get the D. So you see, I still have a 2 cross 2 grid. And the beautiful thing is that number of measurement required is less because combined neighborhood of this path is less. So how to visualize that? You see that combined neighborhood, that one, this path is in any case, it's connected. So 4 has only this neighborhood extra 5, 7 has extra path 8. So this is where you have to do the measurement. But here you have 5 has 2 neighborhood, 8 has 2 neighborhood, and number of combined neighborhood, if you just calculate, you will see that the shortest path has more combined neighborhood. Okay, now I tell you about some other problem. So this is called bottleneck. So far we were trying to create entanglement between 2 nodes, so 1 and 6. So now if there is a protocol which demands, so the protocol is arbitrary for me. The protocol demands that simultaneously 1 and 6 has to be entangled and 2 and 5 have to be entangled. So there are this 2 green point has to be entangled and these 2 red points have to be entangled. So along the path, this 4, 3 cannot be avoided. So 4, 3 exists along the path. So simultaneously, this 1 to 6 entanglement creation and 2 to 5 entanglement creation requires access of this. So this is called, this overlap is called bottleneck. So how to remove this bottleneck? So there was a nice paper, and where it was shown that this kind of network is called butterfly network. Why it is called butterfly network? You just consider that 1 and 2 arm is a little bit longer, and 5 and 6 arm is a little bit longer than 3, 4 arm. Then it will look like entangle, look like a butterfly, a smaller line. So that's why it's called butterfly network. So now there is a transforming a grid graph to a ring graph. There is a nice way. So if we do local complementary operations in sequence like LC1, LC2, LC1, so the left hand side 2 cross 2 grid graph becomes this, and the dotted line, which is the rest of the graph, remains. So what happens? 3 to 4 line is removed, the edge is removed, and 1 and 2 swap. So I'll show you the beauty of this. So now you look at, so keep this in mind and look at this butterfly network. So what happens in this butterfly network? So 1 and 2 swap. So 1 goes up and 2 comes down. So their sequence is changed. 1 goes up, 2 comes down, and then 1 goes connected to 4, 2 gets connected to 3. So 2 gets connected to 3. You see the ring network, and 1 gets connected to 5. Everything remains same. So now I have this ring structure, and where there is no superposition in the path. So you see, you can connect 2 and 5 just by removing 3. Apply local complementary operations here, and you can connect 1 and 6 by removing 4 and applying local complementary operations. So the bottleneck problem is removed. But is it removed only in butterfly network? Can I do it in some other cases? So we just show quickly something. So this is a little complicated one. So you now have 2 rows and 4 columns. So there is another extra line. So these are called butterfly-like protocol. But in this case, if you convert it, so once you apply this LC1, LC2, LC3 sequence and remove 3, 4, so they got interchange. And once you remove this 5 to 6 line and 7 and 8 got interchange, so then you have a circular structure, which is this. But this circular structure, you know that if you have to go from red to red, the green node is between. And if you go from green to green, the red node is between, whatever way you do. So bottleneck problem cannot be removed here. So though in butterfly network, simple butterfly network, that's the simplest grid network, I can do it. I cannot do it in general. Now we increase it. So I'm just increasing the butterfly network's complexity. So here I had a 1 line in the between. Now I have 2 lines, and now I'm going to 3 lines. So you see, this is interesting that when there are odd number of lines, somehow I'm able to, in several steps, I can create this entanglement and bottleneck problem is removed. But when there was an even number of lines in butterfly-like network, the bottleneck could not be removed. So we have recently done several theorems related to this. So this part was the main part which I wanted to tell quickly, and I mean slowly. And now I'll tell, maybe next 5 minutes, I'll have a quick glimpse of other things which we do, but that will be just a quick glimpse. So QIQT is discussed so many times in any of this conference, but QIQT itself is not an application. Application is communication. In QIQT, we are just creating the quantum key, distributing the key, and there are layers of things. So first I have to authenticate. Alice and Bob has to know that they're talking with each other, and if there is a third party, and then only after authentication, main part of the BBIT4 protocol, etc. works. And after that, you are using that key for communication, and that's the application. So Bennett and Brassard was known about these authentications and used the WC81, which is a classical authentication. Now the question is, if the authentication is classical, can I have a secure quantum communications completely? Or we always need a classical component. And if there is a classical component, it's not unconditionally secure. So what is its impact on the overall security of the QIQT? So till now, all the commercial products use classical authentications, but there are several schemes of quantum authentications which have been proposed recently. And there are schemes that you can go do the applications directly. So one such scheme is called quantum dialogue. So quantum dialogue, why I'm talking about quantum dialogue, because our quantum dialogue works have connections with ISAR Kolkata, means we do part of this in collaboration with Professor Panikrai. And so in quantum dialogue, Alice and Bob shares a Bell state in the beginning. So this is an application of entangle. And one particle, so what Alice does or Bob does, before sending the second particle to Alice, he applies a Pauli operations just like dense coding and send it to Alice. And Alice applies another Pauli operations to code her information and send it back to Bob. And then Bob does a Bell measurement and tells the outcome, publicly announces. So now, suppose Alice has applied X, which corresponds to 0, 0. Bob has also applied X, which corresponds to 0, 0. Then X times X is identity. So the state remain unchanged. But when the state remain unchanged, it can happen in 4 different ways: XX, YY, ZZ, II. Yeah. So Eve does not know any fraction. So Eve does not know who has applied what, but whereas Alice and Bob knows that whether what she has applied or what he has applied, so they can guess what the other person has applied, and that's how message can be communicated in both ways. So if we can communicate message both ways, then I can do messaging in one way also. So, and that is what is called quantum secure direct communication. So these are the schemes which does not require prior generation of key. And if I can do QSDC or deterministic secure quantum communications or direct communication without prior generation of key, then instead of sending a meaningful message, I can send a random key, and that will lead to QIQT. So in principle, I can do QSDC, I can do QIQT if I can do quantum dialogue. And these are always applications of course, there are some single particle based things, but mostly these are applications of entangled states. So we find out that what are the minimum requirement, what kind of Pauli groups they form, and then we show that it's not only that Bell states, So all these states, 4-qubit cluster states, 4-qubit W states, all this can be used for quantum dialogue. But the message is not that, because the talk is about entanglement. So we are showing that these are the entangled states which can have applications in generating quantum dialogue. So is quantum secure direct communications. And now coming back to authentications. So in our recent paper with Arindam, who is also in the audience, we have shown that authentications protocol can be classified in many different ways, and there are schemes of quantum identity authentication. So even this part we can reduce from classical dependence and go for quantum. And all these schemes of QKD, quantum error corrections, QSDC, DSQC, etc., can be used for quantum identity authentication. So where entanglement come into the role? So we have already described some simple QSDC schemes. So in or you can remember ping pong protocol. So if such a protocol is there, and Alice has a previously shared secret, he can send that to Bob, and Bob can check that, and that's how one can make authentication. So that's the simplest way to view, but there are of course complicated way to view, and we designed several of such protocols. So this is an entangled state-based protocol. I don't have time to describe, but the message is that quantum identity authentication is a less discussed aspect, which is required for QIQT, and which can also be done using deterministic secure quantum communications protocol. And so if you are interested, just see the reference below, and these are applications of entanglement. So I'll not talk about security proof, etc. So several things like quantum secure direct communications, controlled discrete secure semi-quantum communications, where some of the users are classical, e-commerce, etc., can be done using entangled. So the message is that, if I make a summary, so there are several tricks like majorizations, entanglement routing, and applications of entanglement is very broad. Entanglement can be generated from many different windows. Theoretically, it can be seen through Hillary-Juberi Duan criteria and traditional quantum optics calculations, where you solve Heisenberg equation of motions and find out Hamilton. I mean, when you know the Hamiltonian, you can find out the time dependence of the field operators and find their expectations value to check the entanglement exists or not. And then you can use those entanglement for various tasks. And as the tasks are gradually, the field is getting matured, we need now the larger entanglement than Bell states. We want to distribute them. We want to keep to quantum internet or quantum cryptography involving multiple parties. So in all such cases, entanglement routing will play a very crucial role. And what we have done in most of the time in this lecture is try to give you an idea about some new results on entanglement routing. So I'll stop here, and if you have any questions, you can ask.
Thank you, Anirban. Thank you for making the difficult things in the simplest way. So since you have made the thing simpler, so I expect from the participant that they have understood the thing, and maybe they have a lot of questions. So any question from the participant side?
Ranjit, please unmute and
Can
speak.
I ask a question? Thank you.
Yes, sure.
Yeah. Thank you for your talk. I have one question. Do you have any plans to consider decoherence or noise mechanisms in your theory which you have shared with us, or the noise mechanisms are not significant?
No, means noise mechanism is always present, and we handle decoherence in many other situations, but as far as entanglement routing is concerned, so this activities we started about a year ago, and still the handling complicated graph is pretty difficult, and so it's in an early stage too, but certain genetic results exist and we know how to handle it, but in the theorems we have not included. Theorems are in ideal situations, but there will be some local errors because of that noise, and in finally in entanglement the traditional routes of purifications, etc., can be made to create that entanglement. So traditionally you have methods for doing entanglement purifications and entanglement concentration. So noise will create some problems, and then you can implement those purifications and implement purification schemes.
Thank you. Sorry to say, thank you for your nice talk. Sorry, I forgot to say thank you for your nice talk.
Any other questions? So, Anirban, may I ask you a question?
Sure.
Whenever you were talking about this entanglement routing problem, so you have talked about the shortest path connecting the nodes. So, and then you have.
No, but in one case, we have shown that the shortest path is not giving the best result. So we have.
No, my question is something different. So you have talked about shortest path. So can we apply the shortest path algorithm that already exists in the graph theory? Like Dijistra's algorithm or Prim's algorithm, can we apply there to find out the shortest path between the nodes?
So, I mean, kind of network means we are doing so far means they're very easy to find out because it's not big. So, means you need.
But there is an algorithm, no? There is an algorithm for finding the shortest path.
Because the problem size which can be handled at this stage are so small. So, I mean, we have not used such algorithms. Means we have written our small code and just a mathematical code which looked at. So I don't know means whether my code maps with any of the algorithm, but I have not compared with any algorithm. So the way we have done is I wrote that develop those state vectors, means the kind of vectors I have shown, means my mathematical code makes those, and then we calculated the combined neighborhood and the path length also. So this means my code is 5-6 lines, but we have handled only. So it may happen that my code reduces to one of the algorithms which you were saying, but that I have not checked.
Maybe. So the problem is that the state is given to you, and then from there you have constructed the graph.
Yes. I mean, this is a graph state. Means the graph state exists between this, but the points are not entangled, and then we are trying means how to get entangled. That's the basic definition of the entanglement routing problem.
Actually, I am asking.
Most of the questions are like what we can address at the moment is grid kind of network. So I show this bottleneck problem. So in bottleneck problem, then some of the grid graph can be converted to ring graph. So general validity in some of the theorem, the question is about general validity, that it works in other network or not, whether it's restricted to grid network or not. So examples means like when we visualize, the visualization is pretty straight, but proving the theorems are not that straight.
No, actually, I am asking this question because in the literature we found that there are means they have developed the criteria from where they have just considered the graph, and from there they have constructed the density matrix just by using the Laplacian. Okay, so Laplacian is a positive semi-definite matrix, and if we divide digits by the total number of degrees, then trace will be equal to 1. So it satisfies all the properties of the density matrix. So this means that whenever you have some graph, then you can always construct a density matrix. Just as you said that grid graph is there and some other graph is there, but recently we have shown that there also exist, means if some density matrix is given to you, then also you can construct the graph. So any density matrix. So it is not like that if some graph is there, then from there you can construct the density matrix. We ask the reverse question.
You are talking about a different problem. I'm talking about a different problem. So our problem is that there are nodes. So nodes can be persons, means like in cryptographic network, there is Alice, Bob, Charlie, and David, and so on. So there are there are connections when some people are connected, some people are not connected. So this kind of topology you see even when you look at IBM quantum computer. So if you think of a topology of an IBM quantum computer, all the qubits are not connected. So if those qubits which are not directly connected and you want to share entanglement between them, so then that is the entanglement routing problem. And in entanglement routing problem, a protocol is more, there are two algorithms. The one which is more efficient will require lesser number of measurement, and when it will require lesser number of measurement, it will expected that it will keep the rest of the network intact, because the collapse on measurement will destroy, and the resources means how much resources you can keep and with what is the minimum number of measurements you can do it. That's the task. So here we start with the graph state. So we know the density matrix. Yeah, and we know that means this local operations, which operations has what impact on it. So then these local operations are like my tools, means which will implement, and using these local operations I have to achieve the task. So that's the definition of the problem. So the problem you are talking about and the problem I'm talking about are not exactly the same.
Okay.
Though both involve graph, but it's not the same problem.
No, actually, what I understand from your comment is that you have just considered a graph that is, and then constructed a density
Yeah,
matrix.
means the
This is the way
consideration
of,
is that it's a simple graph.
yes,
It is not undirected. It's a simple graph. And
undirected simple graph.
there is a graph state. Graph states corresponding to quantum state is a graph state. The graph, mathematically, it's a simple graph. And then there is a graph state. But now in the graph state involving all the corners or all the qubits, because if it is a 16 node graph, it's a 16 qubit graph state. And then I choose two arbitrary point in that, and then I want to create an entangled, and which entanglement that has been told to me. Whether I want to create if there are two nodes, I'm creating a Bell states. If there is a three nodes, I want to create GHG states. If there are five nodes, I will create a 5-partite GHG states. So the question is, what is the minimum number of measurements through which I can do that? And whether that, and even if there are two cases, they tie that minimum equal number of measurements, equal neighborhood, then which one leaves the resources more intact? And there we have shown that if we write path vector, and the one which is measurized by all other path will give at least the best result. I mean, there may be other path which is also giving the equally good result, but at least the one which is giving, you cannot beat the one which path vector which has been measurized by others.
Okay, so just a quick question. How you measure, how you find out that whether the resulting state is an entangled state? Means after
Oh,
after operation, after every
no,
operation.
means,
After measurement.
means when, so those things explicitly is not written, but you means you can, that mathematics follows pretty straight, and after, because after every operations, these operations are well defined, this gen operations and LCD means, so you can write the states, and then it's just like applying a gate. I mean, it follows that stepwise, that how the density matrix is evolving, and I can trace the density matrix. But I can work, I mean, for small network, I can work on pen and paper, and for bigger network with some small code in Mathematica, means it gives me the final density matrix.
Okay, thank you, Anirban. So if there is no other question, then let me thanks to the speaker again. Thank
So
you.
I
Thank
just
you.
want to make one small announcement, because assuming that there are some MSc students in the gathering, means like if there are MSc students, like we are looking for PhD students, and incidentally, tomorrow is the last date. So if anyone is interested to continue theoretical quantum information or experimental QKD or other things which happens in our department, like material science and things, just visit the institute website. And if anyone, especially in this group, if anyone is interested to do quantum computing, quantum communications, please apply quickly. This year's means our ending date for PhD applications is tomorrow. And like Satish is here, means there are a couple of students in our group who actually came from QIQT, but when this was in physical mode. So we met students there, offered, and then they eventually doing PhD. So anyway, I'll stop here.
Okay, thank you, Anirban. Over to the organizers now.
So this session ends here. The next session will start from 3 p.m. with Dr. Suranjana Bose. Thank you for participating, everyone.